One of the skills that is important to learn in this chapter is how to write a rate expression. And a rate expression is different from a rate law, and that's different from an integrated rate equation. And we'll get to those in a little bit. But a rate expression, how do you know if you're asked to write a rate expression? Well, you'll see something like express the rate. So we learned kind of the generic form for this, and so we're going to apply it now to this equation. And so we always write rate equals, and it's going to be reactants disappearing and products appearing. So when reactants are disappearing, we always include a minus, and it's the change in the concentration of that species over a change in time. Remember, that's what rate is, change in a quantity as a function of a change in time. Now I left some space here because we have to incorporate coefficients as fractions. So since hydrogen concentration is decreasing, we have a minus, and since there's a coefficient of 2 in our equation, that becomes a 1/2 in our rate expression. So rate expressions can be written for any species in your equation. And this is different from rate laws. Rate laws only deal with reactants. Rate expressions can deal with the disappearance of reactants or the production of products. And the rate, again, since it can be expressed with any of these, and the rate is going to be some constant at a certain time, we can set these all equal to one another. So for oxygen, again, oxygen concentration is going to be disappearing. It's a change in oxygen concentration as a function of a change in time. No coefficient means no fraction in front here. And we don't typically write a positive. Positive is implied, but just to remind ourselves that water vapor is appearing in this chemistry here. Coefficient becomes a fraction. Change in the concentration of water, it's a function of a change in time. So that again is how you'd answer part A, how you would write the rate expression. So that's kind of one part of this writing rate expression skills. The other part actually has to do with some quantitative aspects of this. And what it usually entails is you will be given the rate of disappearance of one of the reactants or appearance of a product, and it'll ask you about the rate of another species. And what we really have to do is then use this as an equation and put in pieces that we know. So again, the rate for oxygen decreasing. So they tell us this piece. They tell us that this is 0.23 moles per liter second. Again, this has to do with molar per second. That's what those units are. So they give us this piece, and we want to know what is the rate of H2O increasing. Remembering that this rate is equal to 1/2 of what we want to find. So let's just call that X. So simple algebra here allows us to solve for X, and we're going to get 0.46 moles per liter second. A real classic mistake that students make here is they actually go kind of in the opposite direction. They'll actually end up dividing this by half because they'll see a half here and they'll think that they're supposed to divide it by half to get the answer. But if you treat this like an algebra problem, you tend to get the right answer. And if we look at this problem and look at our equation, it should make sense. So if this is decreasing at a certain concentration, the reaction stoichiometry tells us that we make twice as much water vapor. So we would expect that the rate of its production would be twice as fast. Some homework problems will go through how to handle, well, what if you do have a coefficient in front of here? Remember, this is the term that we're solving for. So if, for example, there was a coefficient in front of here, we'd have to have that coefficient in front here and then solve it algebraically just as we normally would.